The MOSFET, or metal oxide semiconductor field effect transistor, is the basic building block of modern digital circuits. Here is a schematic of the physical construction of an N-channel MOSFET and a P-channel MOSFET, and here the circuit representation. The basic idea of how a MOSFET works is as follows. The source, the device has three terminals, basically the source, the drain, and the gate. The source and the drain are in an unactivated state. The source and the drain are not connected. That is, electrons from the free electrons in the N plus wells in either the source and the drain cannot flow between each other. By applying a positive voltage on the gate, minority electron carriers from the P region migrate to form electrostatically to form a channel bridging the source and the drain, which then allows current to flow. Similarly, in the P MOSFET, applying a negative voltage onto the gate electrostatically attracts free holes, that is positive charge carriers, to form a channel that bridges the source and the drain, which therefore allows current to flow between the device. Therefore, conceptually, the MOSFET acts as a voltage control switch. The application of voltage of a positive voltage in the N MOSFET would close the switch, and we can represent the MOSFET schematically as a switch in series with a resistance, where this resistance refers to the resistance of the channel that's formed. In 3 dimensions, this device looks something like this. This is bulk semiconductor. And let's say, taking the N MOSFET as an example, this is an N plus well. This is an N well as well. This is the source, this is the drain. And an oxide, the silicon oxide is then deposited in the region bridging the two, the source and the drain. And a metal layer is deposited on top of the oxide. Now, current, when a positive voltage is applied onto the drain, the channel is formed, and the channel actually runs right under the device. So the current flowing across the channel actually resembles a sheet of current that actually connects the source to the drain. This dimension, which is the length of the channel, is frequently abbreviated as L, and this dimension, which is the width of the device, is frequently abbreviated as W. Now, to use a MOSFET as a switch in digital circuits, the FET may actually be connected in 2 configurations. Taking the NMOS as an example, we could have a resistive load here and connect the NMOS this way, or we can have an NMOS in this configuration with the resistive load at the source, and the equivalent circuit model, the equivalent switch model would be something like this. Okay. Conceptually, these 2 circuits function the same way. They kind of look the same, but there are important differences in the way they function. Remember that the NMOS relies on a positive voltage to create a channel, which then acts to close the switch and provide a conducting path for current. In this configuration, the NMOS is known as a pull down, because when the MOSFET is connected, the output node, the voltage of the output node gets pulled down to logic 0 or ground, because charge is sunk through the MOSFET. Whereas in this configuration, the MOSFET is known as a pull-up device because the application of positive voltage here forms the channel and closes the switch, and the output node here is then pulled up to VDD because current then flows to the output from VDD. However, both devices do not perform similarly. The NMOS is a strong pull-down device and a weak pull-up device, because take note, as the voltage of this node here rises during the pull-up, the net voltage seen on the gate, which generates the channel, reduces because this voltage rises, and the voltage difference here reduces, resulting in a gradually weaker and weaker channel. This means that this is analogous to a situation where, as this pull-up is happening, the resistance is actually getting larger and larger, which then slows the pull-up in this way. And therefore, NMOSFETs are typically used only in as strong pull-down networks, but not really used as a pull-up network. So, what gets used as a pull-up network? Well, there is the PMOS. Because notice, by applying a negative voltage here, which is and this is the source, this is the drain, which is so this voltage difference here determines the strength of the channel. The MOSFET, the PMOS, then acts as a strong pull-up device, but it is a weak pull-down device. So for configuration like this, it's not preferred. Notice another thing. When the MOS, in this simple unitransistor configuration, when the PMOS or NMOS is engaged, when the channel is present, there is current continuously flowing in the device, that is dissipation of power, while the MOSFET holds a steady state. This is of course undesirable because we are actually extracting, absorbing power while holding a state. So power is being consumed without doing any useful work. And this then leads to the idea of designing a complementary circuit called the CMOS, where we use a combination of NMOS and PMOS to provide the pull up and pull down. And the advantage of this circuit is such. When the digital circuit must be pulled down, that is when a positive voltage is applied here, the pull down occurs through the strong NMOS, and so it's very rapid. But when a pull up is desired, the pull up happens through the NMOS, the PMOS, this way. And because the in the pull up and the pull down state, there is no continuous path from the VDD to ground. That is, there's no continuous path from VDD to ground. Power is not consumed in the CMOS circuit when it is holding a steady state of either logic 1 or logic 0. So power is only consumed during the switching operation, in the briefest moment when both channels are partially on, when they transition from a pull up to pull down state. So the CMOS architecture, the CMOS configuration actually is used and is very popular in VLSI design today, because of the unique strong pull-up and pull-down nature of PMOS and NMOS devices respectively, and also as a means to save power consumption. That is, power is only consumed during the switching of the logic gates from logic 1 to logic 0, from one condition to another, and not during standby when the device is actually holding state. And these are two very desirable situations to have.